So we have drawn a fluctuating torque diagram for a crank, and we have got the energy, that is kinetic energy of the crank or the flywheel, the crank flywheel assembly, crankshaft flywheel assembly. This energy we have got at different instances in the crank cycle. Okay, so the max you can calculate the E at different points in the crank cycle, and you can get a maximum value. So this maximum value of E, maximum energy of flywheel, is called the maximum KE point, max KE point, and this is where the maximum speed of the crankshaft occurs. Maximum angular speed of the crankshaft. Similarly, you will have a minimum energy point, and for the minimum energy point, the minimum speed of crankshaft will occur. So if you know the points for the maximum minimum energy, or if you know the minimum energy or maximum energy, you can directly calculate by energy equal to half I omega square for a rotational body. So you know the moment of inertia, and you can calculate the angular velocity. E equal to half I omega square. And what about fluctuation of energy? So the difference between the maximum energy, fluctuation of energy, I'll just write it here, fluctuation of energy is difference of max energy and minimum energy. So you have the energy at different points in time. So this value is the maximum fluctuation of energy, maximum energy of flywheel minus minimum energy of flywheel. So you know the energy at different time instances. This is called the maximum fluctuation of energy. And now we have also a coefficient of fluctuation. So the coefficient of fluctuation is defined as maximum fluctuation of energy divided by the work done per cycle. Work done per cycle. So you'll have a cycle, you'll have a fluctuating energy, you'll have a mean. You can calculate the work done per the cycle by multiplying the mean torque with the cycle angular displacement, maybe 2 pi or 4 pi. So that is the work done in a cycle, which is the work done into the rectangular area, and then you have the fluctuation. So you can get the fluctuating energy. So you can get the maximum fluctuation of energy, the maximum value of Ke energy of the crankshaft at any point, and the minimum. And you can take the maximum fluctuation of energy divided by work done per cycle, which is a way to normalize it. So you get a coefficient of fluctuation. So you can compare two different shafts by this using the coefficient of fluctuation. How much fluctuation is occurring in two different designs, since we have normalized by the work done per cycle. Similarly, for the angular speed of the crankshaft, the ratio of the difference of maximum and minimum speed is called maximum fluctuation of crank speed is max crank speed that occurs at max energy of the flywheel minus minimum crank speed that occurs at the minimum energy of the flywheel. And similarly, for the speed, we have defined a coefficient of fluctuation of speed. This is defined as max fluctuation of speed divided by mean angular velocity. So the mean speed, that is omega. So maximum is, let's say, Omega max, the minimum is omega min, and omega is mean. So coefficient of fluctuation of speed will be omega max minus omega min divided by omega. Similarly, for energy, let's say the kinetic energy, K E max, and so for energy we have coefficient fluctuation energy is equal to Ke max, which is much straightforward to follow. Ke min divided by Ke mean. So mean Ke is work done per unit cycle per unit time. Now we come to the second section on the category of flywheel. That is where the numerical part of this chapter lies. Size of flywheel. How do you size a flywheel for a known fluctuation of energy and a known specification on what is the maximum allowed fluctuation of speed. So input for sizing of wheel is fluctuation of energy. This is known from the engine. This we cannot do much to control this given quantity. And the second input is allowable fluctuation of speed of the crankshaft. So this is also imposed by various requirements such as like if the engine is connected to a generator, it can have angular velocity fluctuation within some limit. Otherwise, the frequency of power generation will change. Or if you have a mechanical drive, there also some specification will be given on the speed and the limit in which the fluctuation is allowed. So these two will be the inputs, and then we can go on designing the flywheel. So flywheel basically works on the principle of inertia. So due to inertia, the flywheel inertia is a property of the material being in motion unless it is stopped by an external force, and hence the velocity cannot change much for large inertia items. You need to supply large inertia of flywheel. So since your force is equal to mass into acceleration in angular term, which is the moment of inertia into angular acceleration I alpha in angular, so the force in the angular term the torque is equal to I alpha. So you need, if you have very high I, very high E I moment of inertia, then alpha will be small. So the acceleration will be small and then the change in speed will be small. So this is the main working principle of a flywheel. Flywheel is to provide inertia to the crankshaft. So that is the basic funda. Now the crankshaft, you can see different type of flywheels attached. There are two types of flywheel. One is a disc type and another is a rim type. Rim with arms, rim arm type. So this type is plain disc of metal, and rim arm is having like various arms like this, and there is a heavy metal sheet attached at the end of the arm. So normally the all the this type is arm type, arm rim type. So in this type, all mass is practically concentrated at rim only. So the mass of the arm is very less, and the moment of inertia is still less because they are closer to the center. Now, for any of the two designs, whether it's a disc type or arm type, by geometry and mass distribution about the center, we will be able to calculate the moment of inertia. Calculate I, that is moment of inertia. Mass into radius integration over whole domain. Okay. So this will be a given quantity, or you will be asked or final answer in some cases. So in some cases, you will be knowing the fluctuation of energy, uh, fluctuation energy, and fluctuation of speed, and you will be asked to find out I. In some cases, energy fluctuation I will be given, and you will be asked to calculate the fluctuation of speed. So basically, we have three quantities, and we want to know the relation between these three. So now we'll go on with the derivation of sizing of the flywheel. So let's say I is given, that is moment of inertia of the flywheel. Then we have omega 1 as the maximum speed of crankshaft. So this will be equal to 2 pi and 1 by 16. So where n1 is maximum RPM of the crankshaft. Definitions are simple. And then we have omega 2, that is minimum speed of crankshaft. This will be equal to 2 pi and 2 by 60, where n2 is minimum RPM of the crankshaft. Then we have omega, which is mean speed of crankshaft, which is equal to 2 pi n by 60, where n is mean RPM of the crankshaft. And then we have E as the kinetic energy of crankshaft at mean speed, that means omega. Then we have EF as equal to maximum fluctuation of energy. So this is a point quantity. It will come from the turning moment diagram that we have described just now, and usually it will be a given quantity. Because calculation requires a lot of detailed insights in the subject of turning moment diagram. And then we have Ks, that is coefficient of fluctuation of speed. So this will also be a given quantity from the design point of view. The designer will specify how much the RPM of the engine can vary according to the generator or the drive which the system is driving. So this will be a design requirement to be met. And this will come from turning moment diagram. So now from our definitions, we know that the kinetic energy in an angular system is equal to half I omega square. So maximum kinetic energy of flywheel and crankshaft. We'll talk about crankshaft and flywheel only now in all our derivation. So I'm putting off that symbol. Maximum K will be half I omega 1 square, because omega 1 is the maximum speed of the crankshaft. Similarly, the minimum kinetic energy of the system will be equal to half I, the moment of inertia will remain constant, omega 2 square, that is the minimum speed of the crankshaft. And the difference between max Ke minus min Ke, minimum kinetic energy, is equal to fluctuation of energy, equal to maximum fluctuation of energy. So we put our derivation here, half I omega 1 square minus half I omega 2 square equal to the fluctuation, maximum fluctuation of energy is given. It is a known quantity EF. So we'll put it here. EF, the maximum fluctuation energy. Now in this quantity, in this calculation, we take half I outside. We'll have omega 1 square minus omega 2 square, that can be decomposed as omega 1 minus omega 2 multiplied by omega 1 plus omega 2. Because a square minus b square is a minus b multiplied by a plus b. So here you can see that uh, omega 1 minus omega 2. So you have the definition for coefficient of fluctuation of speed, fluctuation of angular speed is equal to omega 1 minus omega 2 divided by omega. So the coefficient of fluctuation of speed, we have defined it here as Ks. This is also a specified quantity from the design engineer. So this is equal to Ks. So hence omega 1 minus omega 2 will be equal to Ks into omega. So substitute this value in this equation, we will get half I Ks omega multiplied by omega 1 plus omega 2. So V is equal to EF. So here in this equation, omega 1 plus omega 2 divided by 2 will be somewhere near the mean speed. So we will not go into complex cases where the maximum minimum is very different from the mean. So here we will take that omega 1 plus omega 2 divided by 2, the maximum and minimum average is equal to mean speed. Of course, this is an approximation. This can be different for different cases, but for our start and simplified case, we will take that the average lies at the center of the maximum and the minimum. So from this quantity, by substituting this relation, we get half, the half will go now, we will get I Ks omega square is equal to EF. So this is the final formula for flywheel design. So let's explain the importance of this formula now. So this is the final formula. You know the maximum fluctuation of energy, you know the coefficient of fluctuation of speed, and you can find out either the moment of inertia of the flywheel which will be designed, or if you otherwise if you know I and Ks, you can calculate EF, or if you know Ks and EF, you calculate I. Any among the three. The omega will be known quantity normally. So we'll see the application of this formula in the coming numerical examples. But from the formula itself, you can see that I omega square is somewhere near the mean kinetic energy of the flywheel. So mean kinetic energy of the flywheel multiplied by coefficient of fluctuation of the speed is equal to coefficient of the fluctuation of the energy. So coefficient of fluctuation of speed is a non-dimensional quantity. It will be in some percentage. So the percentage variation of energy is somewhere near the, and I omega square, the half I omega square is the mean energy. So percentage variation of energy will be the maximum fluctuation of energy divided by mean energy. Mean energy of the system is half I omega square. So if you see from this formula, this will be equal to 2 Ks. So hence the percentage variation in energy is 2 times coefficient of fluctuation of speed. Speed. This is another interesting insight that we get from this equation. This coefficient of variation of energy, the percentage variation in energy is also called coefficient of fluctuation of energy. And since we have termed the coefficient of fluctuation of speed as Ks, we'll term it Ke. So we'll get the identity that Ke is 2 times Ks. Before going forward on numerical section, we will consider one final topic in the theory, that is calculation of hoop stress, or hoop stress is also the circumferential stress in simple words, in rim of a arm type flywheel. So arm type flywheel is formed by various arms that are connected to a rim, and the whole of the mass of the flywheel is supposed to be concentrated at the rim. So you have a rim here, and all the mass is concentrated on the rim, and then you have various arms from the center that are connected to the rim, and the mass of the arms is negligible. Negligible. So in this case, if the flywheel is rotating with angular speed of omega, and the radius of rim is r, then what is the hoop stress or the circumferential direction stress in this direction in the gear in the rim? So for that we will take a small element of the rim, let's say this thing, which is having angle b theta, and from center the radius of this element is r, and this angle is d theta, and then the thickness of the rim is neglected. Thickness of rim is negligible. So we will consider that there is no variation along the radial direction. This is the radial direction, and things are constant along the radial direction. So if the hoop stress is sigma on this element, that is circumferential stress, how can we calculate this thing in terms of the mass of the rim per unit volume and the rotational speed omega? So if you take the free body diagram of this uh, small element, it will look something like this. So you have sigma, sigma. Let's say the cross-sectional area of the rim is A. So the force in this direction, around sigma direction, will be sigma A. A is area of rim cross section. So sigma A is that in this direction, sigma A is in this direction. From the center, this angle will be theta by 2, and this angle will be theta by 2. So as you can see here, if you draw a center line, this stress is acting as a theta by 2 angle and theta by 2 angle, because to the total rim, the angle is theta. So actually this angle is d theta by 2 that we are considering here. We have considered a small angle d theta. So if you see the component of this force, the stress force along the radius, you will see that in this triangle, this is sigma A force. This is a component of force along the center, and this is angle d theta by 2. So the component of force along component of stress force along center line is sigma A sine d theta by 2. And similarly for the other side also, the left side also, the angle is d theta by 2 and the stress is sigma A. So it will be sigma A sine d theta by 2. Now these two forces will be counterbalanced by the centrifugal force of the mass. So stress force is balanced by centrifugal force that will act away from center. So the stress force is towards the center. As you can see from this diagram, the component of stress force is towards the center, and then there will be a force, centrifugal force, away from the center. And since this is a free body diagram of a small element on the rim, so hence the forces must balance each other along any particular line. So along the radial line, they should balance. So we will write the formula for the centrifugal force. Centrifugal force is mr omega square, where m is the mass of the rim element that we have considered. So for that we know the volume of the rim element. Volume of the rim element will be the cross-sectional area. Cross-sectional area is A multiplied by length of the element. Length of the element L. L will be equal to r d theta. So this is length of the element. So A into r d theta, this will be volume of the element, rim element that we have considered, multiplied by rho, where rho is density of rim material, right, in multiplied by r omega square. So these two forces should balance each other, the stress force and the centrifugal force. Now we will simplify this expression. We know that for small theta, sin theta approaches theta. Sin theta can be replaced by theta. So since we have taken a small element, infinitely small element here, we are using differential calculus type of convention. So theta is very small, d theta is particularly small. So sin d theta by 2 is equal to d theta by 2. So we will substitute the value here, sigma a d theta by 2 plus sigma a d theta by 2 equal to a r square omega square d theta rho. So the summation will give sigma a d theta equal to a r, and you know that r omega is equal to v, the linear velocity of the rim element. So omega is angular velocity, r is radius, so v is linear velocity of rim, or the circumferential velocity in this case. Circumferential velocity, because omega, this is v, so r omega is equal to v. So here you will replace r square omega square by v square d theta rho. D theta will get cancelled out, a will also get cancelled out on both sides, and you get stress is equal to rho v square. So if you know the material density of the ring material and you know the circumferential velocity, v is equal to circumferential velocity of rim, then you can calculate sigma, the hoop stress or circumferential stress in ring. Now we will move on to numericals in the chapter of flywheel. So we will consider the numericals mainly related with the flywheel design, and the part related to the torque diagrams was basically a theory. So I'll just take the first numerical example here. It is given that there is a pressing machine. So a pressing machine, if you have seen somewhere that there is a motor which is giving the input, and then there is a pressing machine, so which goes and press the job. It supplies some kind of force on the job periodically, and the in later part of the time period it gains energy from the motor. Driving motor motion is continuous, and then there is a pressing machine, the motion is intermittent. For some part of the cycle, if you press the job, then it will come back, then again it will go back and press. The pressing machine is operated by an electric motor supplying constant torque. So in this case, the driver is not an IC engine; it's an electrical motor, and hence it is able to supply a constant torque. But in the present, in this case, the variation of energy, the fluctuation of energy will come from the press. This will lead to fluctuation of energy because the motion is intermittent. Now the motor power is 5 HP, 5 horsepower, and at the commencement, at start of cycle, like we consider a load variation cycle. So load variation cycle that we know in the torque diagram. Here the load is varying, so the torque is varying on the driving shaft. Load variation cycle. At the start, the pressing machine had a speed of 300 RPM. 300 RPM. And moment of inertia of flywheel is inertia height of flywheel is 60 kg per meter, 60 kg meter square. kg meter square of flywheel. So we'll consider that the flywheel is the main element in the driving shaft and the moment of inertia of shaft is neglected. The flywheel is the major contributor and we will do calculation for only flywheel. We will consider the flywheel inertia as the moment of inertia of the entire system. Now it is provided that each pressing operation needs 560 kg meter or joules of energy. So we know from the job what kind of job we are doing. It requires this much of energy and takes 1 second. So job needs 1 second to process. So we have to find a number of pressing in 1 hour. How many maximum pressings can you do with the given configuration, the machine power and the machine RPM, and within an hour, how many jobs you can do to supply this much amount of energy, 560 kg meter. The second part of the question is that reduction in speed after pressing. Just after the pressing, a lot of energy will be extracted from the driving shaft, and this driving shaft speed will reduce. So, what is the reduction in speed? So, consider there is no loss in the system. So, we'll go about solving this problem. So, for part A, we know that this much energy is required for operation, and per operation it takes 1 second. So, total energy supplied per hour, because the question asked is that number of pressing in 1 hour. So, we'll first calculate how much total energy can the motor supply in 1 hour.